Okay, so I want to talk about compact oblivious routing. So this is a joint work with Stefan Schmidt, who is from the University of Vienna. Okay, so what is oblivious routing? First, what is routing in networks? The theoretical perspective. So essentially what we want to do is we want to solve a multi-commodity flow. So we are given an undirected network. So in directed networks, it doesn't really work. Bounds get very bad. So if I'm given an undirected networks, I'm given source-target pairs, and I'm given demands between these source-target pairs. So for example, between these, I want to route 1 unit of traffic. Between these, I want to route 2 units of traffic. And now what I want to do is I want to kind of route a flow between each pair. So I'm allowed to use flow routing, so I'm not limited to routing along fixed paths. And I want to have flows that minimize some cost. So I could decide that I use this single path for the get one, the green one is split among 2 paths, and for the orange one I use another flow. So I want to use flow routing in this network. And if I phrase it like this, it's kind of a centralized optimization problem. So I'm given demands, I'm given this network, then I run my routing algorithm that kind of fixes all these paths, these flows, and then I want to have close to optimal cost, whatever this means. Of course, I cannot do this in routing in a distributed fashion. This doesn't really work because these demands usually they change over time, and I cannot rerun this whole optimization. And now what is oblivious routing? Oblivious routing says, oh, maybe ideally, if I really want to be able to implement this very efficiently in a distributed setting, I want to be independent of the demands. So I want that the routing path should be independent of the demands. And then if kind of I simply use fixed routing tables, I may allow some randomization, and then I simply follow these pre-computed paths. And now the question is, can I still kind of obtain close to optimal cost? So what is the framework? Again, what is an oblivious routing scheme? An oblivious routing scheme specifies a unit flow between every source-target pair. And this unit flow that you pre-specify is kind of just a routing rule, a routing pattern. And now if a demand appears for a specific pair, what you do is you simply satisfy this demand by scaling this unit flow by di. So demand appears with this value di here. You take this unit flow, you scale it up by di, or if di is 0, you scale it down to 0. And then you have a flow that satisfies the demand, and that's what you do. So that's a very natural concept. If you simply get lots of packets for a certain pair, you kind of, all these packets follow these flows. That's naturally then that kind of this unit flow is kind of scaled by this demand. You can view it this way. Now, how do you analyze the quality of such a scheme? I said, oh, can we really get kind of close to optimum cost? That's a question. And this is standard in theoretical analysis. You use what is called a competitive ratio. You analyze the cost of your routing algorithm, and you take the worst case factor by which you are away from the optimal solution. So formally, you maximize over all demands the cost that your algorithm has on this demand divided by the, what an optimal algorithm has as a cost for this demand. So this ratio you want to have as small as possible. And now for oblivious routing, first of all, I need to talk about cost. What cost measures could I look at? For example, I could look at the simplest cost measure. I want to minimize the total traffic in the network. And actually, I would use shortest path routing. And so total traffic in the network, you sum over all edges, the total flow that you send along an edge times the length of the edge if your graph is weighted. So this is what will be the total load. And congestion is another cost measure. You take the maximum traffic along a network link, and this is what you want to minimize. So you maximize over all edges, the flow along the edge, divided by the capacity of the edge. So in the first version, if I have a weighted graph, I interpret the weight of an edge as a length. In the second one, if I have a weighted graph, I interpret the weight of the edge as a capacity, but not in a hard capacity sense. So I'm allowed to send as much flow along an edge as I want, I'm only kind of penalized in this cost function. And kind of this capacity capacity does not give a hard limit how much traffic I can send over this flow, just gives a weighting of the edges. And of course, there exist other cost measures as well. You could look at the A2 norm of the linked loads or something like this, and also for these, there exist oblivious routing schemes that perform well. And now what are the results here? If you look at load, okay, if you want to minimize load in an oblivious manner, you use shortest path routing. That's an oblivious routing scheme. Shortest path routing is oblivious, so it's trivial. You get a competitive ratio of 1. So this is kind of a little bit boring. Now, if you look at this cost measure congestion, it's not clear that actually you could get close to the optimum congestion at all with fixed routing paths. But so in this work, it was shown this was the first oblivious routing scheme that for the cost measure congestion obtains a polyarithmic competitive ratio. So you are at most a factor log n to the 3 away from the optimal congestion that you can get. But this only holds for undirected graphs. So of course, the top result for load works in directed graphs as well. This only holds for undirected graphs. And this has been improved by Helsen, Hildem, and Gao, who improved the competitive ratio. And the first result kind of constructing these routing tables was not polynomial time. This improved the competitive ratio, and this is polynomial time. And in 2008, there is another oblivious routing scheme that obtains a competitive ratio of log n, and log n is the best that you can get. So you cannot get better than log n. So this is because there's a lower bound. So there's a lower bound of Bartel and Leonardi of log n on undirected graphs. And this lower bound already holds for a much, for an algorithm that is kind of more powerful, it holds against online routing. So in online routing, kind of the routing requests appear one by one, and you have to fix the path when a request appears. So in some sense, you can, in online routing, your routing decisions may depend on the demands, because a routing path can depend on previous demands that appeared, but they are not allowed to depend on future demands. But even if you have this dependency on the demands, you can not beat the log n on undirected graphs. Yeah?
I just want to understand, what does it mean to have congestion on an undirected graph? Does that mean you're counting the traffic in both directions as contributing to the load on the link?
No,
I'm just trying to, undirected links, the traffic goes in 2 directions, so I'm just trying to understand what does congestion mean in that context when the graph is undirected?
Undirected is simply, you can use every edge in both directions. So there are some packages that want to use this edge in this direction, other packages that want to use the edge in the other direction. And what is the load of the edge? That is simply the total flow along the edge in either one of these directions.
A single capacity in both directions contribute to its use?
Yes.
Okay, thanks.
And now so in undirected graphs, kind of there doesn't seem to be an advantage, at least asymptotic advantage, if you use oblivious online routing as opposed to oblivious routing. So if online routing at first glance should be superior because you have more power, but this shows kind of, you can get a log n with oblivious routing, and there's a lower bound for online routing. But actually in direct graphs, the situation is a lot different, because there was a lower bound of omega of n for the competitiveness of oblivious routing in directed graphs. So you actually, in directed graphs, oblivious routing is really poor. But online routing in directed graphs actually gets a log n. So there in directed graphs, there is a sharp difference between online routing and oblivious routing. So now, the main motivation is I want to implement these, the main motivation for oblivious routing is I want to implement this in a distributed fashion. But now there is more than just dynamics to implementing something in a distributed fashion. And usually the routers, the intermediate nodes are routers, and routers kind of have maybe severe memory limitations and so on. So another thing that I may want to optimize, I maybe want to have small routing tables. And that's where compact routing comes in. So in compact routing, I want to have small routing tables. And this question comes in two flavors, in two different variants. So what is a model? A packet enters the network at the source, and it has a unique name for its destination. And now there are two variants of this model where this name comes from. So in the first variant, that's the labeled variant, the designer of the routing scheme is allowed to rename all the vertices in the network, and then I can simply, the name that appears is a name that is given to this destination by the designer of the routing scheme. And in the second, this is name independent, so the nodes' names are fixed and cannot be changed. So these are different variants of this problem. And this compact routing problem has been extensively analyzed for if you want to minimize the load. So there are lots of results about this. And what do people look at here? They basically look at the space stretch trade-off. So the stretch is a competitive ratio with respect to the cost measure load. This is called stretch. And then you look at the space. And the space here is the size of the largest routing table at a node in the network. So you don't simply take the space taken by all routing tables, but you want to minimize the largest routing table that you use. That's the space. And there are also additional parameters. What header size do you use? What is the label size if you're allowed to assign the labels? So these are also important parameters. But the most important are here the space and the stretch. And now I just pick very few results here, just 3 of them. Okay, if you have allowed space n log n, then you can kind of implement shortest path routing, because every intermediate node just has a table with containing an entry for every destination, and then the outgoing links that you have to take. So that's a space of n log n at most. And Taub and Zwick, they gave a labeled scheme that obtains a competitive ratio, a competitive ratio of 4k minus 5. And the space was n to the 1 over k. So this tilde here ignores logarithmic factors. So roughly n to the 1 over k. And this is for a labeled scheme. And here, Abraham et al., they showed actually that one could basically more or less get very similar guarantees for the name-independent scheme as well. So this name-independent scheme, of course, you have maybe worse. So it's the same if you don't care about constant factors. But actually here, people do care about constant factors. So otherwise, they wouldn't have written something like 4k minus 5 or so. And but asymptotically, these schemes are very similar in terms of performance. And at least to me, this is surprising that usually I would assume that being able to determine these names will help you a lot. For example, in a grid, usually the name is the x-coordinate and the y-coordinate of a vertex. This is kind of useful if I then want to route. But now in this name-independent scheme, a vertex has a name of A or B, I don't know. So this kind of should make things more difficult, but it doesn't do it in this case. And also there is a lower bound here. Okay, this is lower bound is kind of a conjecture. So Erdős has a conjecture that there exist graphs with GERS 2k plus 2, so the length of the smallest cycle, and omega of n plus n to the 1 plus 1 over k edges. And now if you have a graph like this, so all cycles are long. Now if you want to have a stretch that is smaller than the length of the cycle, essentially what you need to know, you need to kind of store every edge. The routing scheme needs to have information for every edge. And this means the total size of all routing tables need to be the number of edges. And so if you divide this by n, you get n to the 1 over k. So this shows that this is essentially tight if, of course, this conjecture holds. This has only been proven for some values of k. So this is still a conjecture. So this is kind of the state for load. So the previous results for congestion are non-existent. So we looked at this problem. We wanted to look at, can I do this with small routing tables? There weren't any results. So now what we did is we did some work and we did some results. So these are kind of very preliminary results, and they are kind of very simple ad hoc schemes, and maybe in the discussion you can improve them. So, but we look at a different parameter here. So if I'm looking at the space, I want to do the following. I want to allow that the space of a vertex may depend on the degree of the vertex. So why do I want to allow this? So formally what I want to do is, I want to kind of say the routing table is at most alpha times n times the degree of a vertex, and then I want to kind of minimize alpha n. I want to have a small alpha n. And if I want to minimize congestion, this seems necessary, because if I want to minimize congestion, and I have lots of edges available, I should use them all. Otherwise, I'm in trouble. If I'm using just a very few edges, I'm in trouble. And therefore, if I have lots of edges, I need to have large routing tables. And, but it makes sense to say that if I have a node and it has lots of outgoing links, then it should have larger memory than a node that just has a few outgoing links. In particular, if I'm phrasing it like this lower bound from the previous slide by Erdős doesn't apply at all. Because there it was simply say, oh, you need to know all edges. Here I can store information for all edges with an alpha n of 1. And then, of course, you want to have the quality. The quality is the competitive ratio. And you want to have kind of small label size and a small header size. So what I want to kind of the quality should still be polyrhythmic. I want to have a polyrhythmic competitive ratio. I cannot go below log n, of course. I want to have polyrhythmic label size and a polyrhythmic header size. And now I want to kind of sketch how I do this. And we base ourselves, so these routing schemes for Oblivious routing, they come in two flavors. So these schemes, they are based on a hierarchical decomposition of the network that I will describe in a moment. And this scheme is different. What it does is it embeds a bunch of trees in the network. And then basically if you do a routing decision, what you do is you sample a random one of these trees and you follow the path in this tree. This is what this routing scheme does. The problem with if you want to do this compactly, that's maybe very difficult because you need a lot of trees in this scheme. So if a node has to store something for every tree, then you are in trouble. So therefore, we are basing our routing scheme on this. And so what you do is I quickly explain this hierarchical decomposition. So how do the existing Oblivious routing schemes work? They compute a hierarchical decomposition. They take a graph, decompose it into pieces, and each piece is decomposed recursively. And you do this until on the lowest level, these clusters here just contain single vertices. So now if I have this decomposition, this has to be done in a clever way. Now I describe how I choose a routing path. So suppose that I want to route between these two vertices, this source and this target here. And now I specify this routing path in a very strange way. What I will be doing is I will be sending a message from the source, and I will also be sending a message from the target. And somewhere in this graph, these messages meet, and then I get kind of specify a flow from the source to the target. But it's easier to describe this as sending from the source and the target. And I will not send a message to a particular vertex, but I will be distributing this message among a bunch of vertices. So I can either view this as kind of a probabilistic thing that I'm doing, or I'm sending a flow. And I want to also be able to send flows to edges. So if I say I send flow to an edge, I simply assume that maybe for simplicity I have every edge has a vertex in the middle of the edge, and then I send the flow to that edge. So now, how do I send the flow between these two? The first thing is that the source and the target, the source takes a message and sends it to a random one of its outgoing edges. And the target does the same. So the message stays now at a random of these outgoing edges, or if I have a flow, it's distributed evenly among these outgoing edges. Now in the next step, what I do is I'm sending the message from this distribution to the distribution on the parent cluster. And here the distribution on the parent cluster is among edges that leave this cluster or edges that connect different subclusters. So this parent cluster is partitioned into this cluster and this cluster. And now I'm sending the message to kind of a random one of these edges, either leaving the cluster or connecting different subclusters. And then after this, I'm sending the message to kind of the corresponding distribution on this parent cluster. So I'm sending it from this distribution to this distribution. Now, in a moment, I will explain how I do this step. And now, in the end, at the least common ancestor in the tree, I will send the message to the same distribution on edges that leave this cluster or that connect different subclusters. And now, kind of this specifies then a routing path between S and T. And now, what do I do if I want to, suppose I want to route a message from this distribution to this distribution? What I do is I do a two-step process. The message sits at a random one of these edges, and it wants to, afterwards, I want to distribute it at a random one of these edges. So the first thing that I do is I'm sending it to a random border edge of this cluster. This is the first thing. So from this distribution to a random one of these edges to a random border edge. Of course, I'm only doing this for edges that actually want to kind of leave this cluster, that want to route along this edge. And then here at the top, then this is the same. It's sitting at a random one of these edges, and then I'm sending from a random one of these edges to this distribution. So one thing that is important here is if I send a message to random one of these border edges, so all messages in my routing scheme. So now I assume that I get a demand that an optimal algorithm can route with congestion 1. I can scale all demands, doesn't change the competitive ratio. So then the number of messages that I send to these border edges in expectation is 1. This is what a border edge receives. Because every message that I send to these border edges leaves this cluster. If an optimal algorithm can route this with congestion 1, the number of edges should be smaller than the border of this cluster. And so if I'm looking at what I'm doing, for example, at the top here, there is a kind of a message of 1 maybe sitting at these random edges, and it's distributed from, so an edge injects 1 unit, and it's distributed among all these edges. So this is kind of what I have to solve on this cluster. So what happens here is I had the message between S and T, and now I partition the message into many sub-messages, and all sub-messages now look the same. All sub-messages are now routed between this cluster distribution, either to a subcluster, to the border of a subcluster, or in the other direction, or they route from this cluster distribution to the border of this cluster. This is what this whole thing does. And what is about this hierarchical decomposition? The hierarchical decomposition just ensures the following. Define a concurrent multi-commodity flow problem for every cluster. Every edge injects 1 unit, distributes among all other edges. This concurrent multi-commodity flow problem, you want to be able to solve with small congestion. This is what this decomposition is about. So, and what does this paper show? There is such a decomposition such that every concurrent multi-commodity flow problem can be routed with congestion at most log squared n inside the respective cluster. And then if this is true, then if you kind of solve all these multi-commodity flow problems together, the total congestion that you have is just log to the 3n, because an edge is at most contained in logarithmically many clusters. So the height of this tree is logarithmic. And they gave a slightly different property here. So now what I want to discuss is, the thing is, what we do now is we simply take this concurrent multi-commodity flow problem and we try to implement this with small routing tables. So this is the idea. So I encode this solution of the concurrent multi-commodity flow problem for every cluster. Now, how do I do this? So every edge of the cluster distribution gets 2 IDs. So it's kind of an edge that kind of is between different subclusters. It's in 2 subclusters because therefore I give it 2 IDs, this edge. And I distribute these IDs in such a way that every subcluster has a consecutive range of IDs. And now what I can do is, if I do it like this, I can say, oh, I want to route into a particular subcluster. I'm sitting in an edge. I want to route into a particular subcluster. What I do is I'm looking at the range of this subcluster. I pick a random ID out of this range, and I'm routing there. This is the idea. And now a vertex of a cluster has to store the ID ranges of all the subclusters in order to be able to kind of make this decision, which next ID to take. So now, what is the cost? So first of all, how do I label my vertices? I label my vertices by the path from the root in the decomposition tree to the leaf vertex. So every vertex corresponds to a unique leaf vertex in this tree. This is the label that I assign to this vertex. This is kind of very small. So given the source and the destination label, I can compute the path in the decomposition tree. This is kind of easy to do. So then I know the path in the decomposition tree. And now how do I route along this path? Okay, initially the source sends a message to one of its random outgoing edges. That's easy. And now for every upward edge in this tree, what I simply do is I'm sampling a corresponding target, corresponding ID. So I'm sitting at the cluster distribution of Si. So Si plus 1 is the cluster that is higher up in this tree. So I'm sitting at this cluster distribution. I'm first routing to the border of this cluster. But in doing so, what I simply do is I'm sampling a random ID from the cluster border, and then I'm routing to this ID, and I'm following the concurrent multi-commodity flow solution for this cluster. So this has a commodity for this edge pair, and I'm following this commodity. This is very naive. This will be very poor in terms of routing tables. And then if I want to go to the border distribution of Si to the cluster distribution of Si plus 1, I do the same. I'm sitting at a random border edge. I'm sampling a random edge from the cluster distribution, and I'm following the concurrent multi-commodity flow solution that brings me there. Now, what is the problem with this scheme? So, and downward, I do the kind of the opposite. Thus, I change the direction. What is the problem with the scheme? Routing tables are a disaster. So I encode an optimal all-to-all multi-commodity flow, and now competitive ratio is still log to the 3n because I still have the exact multi-commodity flow. It's kind of the same as the theoretical result. Label size and header size are kind of very small. That's fine. But now what I'm doing is I have to the table size is very large because if I have this multi-commodity flow, there are m squared source target pairs. So, and I want to encode a flow for each of these source target pairs, so this is very, very large. So now we kind of try to improve this. So what you do is, instead of simply storing this multi-commodity flow solution, concurrent multi-commodity flow solution, what you do is you, for every subcluster, from the border of a subcluster, you have a flow to the cluster distribution. From the border of a subcluster, you have a flow that brings you to the cluster distribution. And this can be a single commodity flow. And then if I'm sitting at a random node of this cluster, of the border of the subcluster, I can follow this flow, and this brings me then to a random node on the cluster distribution. So this is, I can do just a single commodity flow here. So the number of flows is just the degree of the tree, the degree of the decomposition tree. And now here the competitive ratio still would be the same because I can actually find all these flows. The label size would be fine. The header size also is the same as before, more or less. So now, what is the table size here? The table size is I have just so many flows that I have to maintain. So it's just a degree of the decomposition tree. So now what is the problem with this scheme? The problem here is that I actually don't really know anything about the degree of this decomposition tree. If I'm looking at grids, for example, the degree of this decomposition tree is constant. That's excellent. And I think for many other networks, it's also constant. But if I, for example, take a star, this decomposition tree is more or less a star itself. So the degree will be large. Of course, for a star, I can kind of solve the problem in another way. So I don't really have a good bound on the decomposition tree, on the degree of this decomposition tree. And there comes the next problem, the first open problem. Can I, at least for some graph classes, get a good bound on the degree of this tree? I have no idea. So now I want to have yet another variant where I get rid of the degree of this decomposition tree at the expense of maybe making the competitive ratio here a little bit worse. So now what you do is this, what I described now, works only for unweighted graphs. So what you do is, so the first variant said, oh, I simply store the all-to-all multi-commodity flow problem. Okay, this was too large, too many flows. The second one is, okay, I thought, oh, okay, I do something for every child. Still too many flows. So now what you do is you embed a hypercube between the edges. This is the next idea that comes to mind. So what you do is you say, we assign IDs to the edges as before, as in variant A. And I assume that the number of IDs is kind of power of 2. This kind of makes things easier. And now you embed simply a d-dimensional hypercube for the IDs. You can embed this hypercube with congestion d times log squared n. So between the edges, you can route all to all with congestion log squared n, because you can solve the all-to-all multi-commodity flow problem. And now, if I can route all to all, I can route any permutation, and hypercube is just d many permutations. So I get this d log squared n congestion for embedding the hypercube. And now if I want to route, not yet done, I also apply randomized rounding here. I want to embed the hypercube such that every edge is a single pass, not just a flow. This all-to-all multi-commodity flow problem may give me a flow. So I apply standard randomized rounding. I decompose the flow for every commodity into distribution of a path. I pick a single path. The congestion doesn't really go up. Now things are great. Why? Because the congestion of what I have embedded here is just d log squared n. But every path has weight 1. So how many paths does a vertex see? Its degree times this d log squared n. So the number of paths that a vertex sees is small, so the routing table should be small. And this is actually true. So these are the label size, header size I as before. The competitive ratio here goes up by this factor of D, because I'm embedding the hypercube. And now here, this is actually, the table size is actually essentially kind of the number of paths that I'm seeing, and for every path, so this is the number of paths that I'm seeing, and for every path I have to store a little bit. Now, one thing that I have to also store, I have to store the ranges of the subclusters. And also this I can do efficiently. So if I want to store the ranges of the subclusters, I'm routing all these ranges to a power of 2. And now what I do is I'm sorting the subcluster according to the size of the range. And now what I'm essentially, so now I have range classes. Everything is rounded to the power of 2. I have range classes. And now what I have to do is, this is the range of the whole cube, the whole number of IDs that I have. And now I want to communicate to a certain child, to a certain subcluster, and ask, what is the range of the subcluster? So what I do is I'm first making a binary search here, and I ask, which range class is this child in? So how many IDs does it get? And here I'm storing, for this range class, I'm storing kind of the first ID that starts this range class and the first child. And then I can compute where the range of this child that I want to communicate to starts, and then I pick a random ID from this range. So this also is kind of the routing decisions would be log m time. Unfortunately, this is just for unweighted graphs. So we can improve this. We can also show something for weighted graphs, but only if the weights are kind of from 1 over, weights are 1 and W. So W now may be very large. Yeah?
Weight corresponds to capacity.
Weights correspond to capacity. And now why is it problematic? Why are these large weights problematic? So essentially, I have a subset of the edges, and I want to maybe embed a hypercube between a subset of the edges. So what I did is I simply solved the all-to-all multi-commodity flow problem. I did randomized rounding on this. And then this gave me paths of weight 1. But if I have edges here that have a very large weight, this means a lot of paths may go through this edge. And now my routing tables, if they have to store something for every path, the routing tables will be very large. So this is a problem. And now I just, yeah?
If your goal was alpha n times weighted degree of the...
If I have alpha n times weighted degree, then everything's easy. Then this is not a problem. But I want to have alpha n times a degree. And now I just, so one method to kind of solve at least a subproblem, suppose I just want to embed a hypercube between the light edges. So I have a subset of the light edges, they have weight 1, and I want to embed a hypercube between them. So now there's one trick. What I do is, instead of embedding a hypercube directly, I first embed an expander between them. And for this expander embedding, I'm using what is called a cut matching game by Karao-Vazirani. So what does this do, this cut matching game? It embeds an expander, at least for our scenario, it embeds an expander in a very specific way. So the expander is embedded by a series of matchings. So I have polylogarithmically many matchings, and these are arbitrary matchings between the subsets of vertices that I want to connect. So what happens is, I'm partitioning my light vertices into 2 subsets. And then I compute a matching between these subsets, any matching. Then I partition the subset into my light vertices into another 2 subsets, subsets of even size, same size. And then I compute another matching. Any matching will do. And then I partition them in yet a different way, and I compute another matching. After I do this log squared n many rounds, I will have an expander. And now why do I want to do this? Because I can store these expanders very efficiently. I cannot, at least I don't know how to store arbitrary routing paths, but these expanders, by matching, I can store such a matching very efficiently. So how do I do this? How do you get this matching? So what you do is you compute the flow from S to T, and then you decompose this flow into matching edges. This is how you compute the matching. And now what I do is I make this decomposition in a step-by-step process. So if I have this flow, I get a directed acyclic graph kind of following the direction of the flow. And now every unit here of flow that I'm seeing, I'm assigning it the idea of a path. And I do this in a step-by-step. So suppose that I already assigned IDs to these parts. So there is some path with ID of 100 coming in. This ID has 7, and here's a path of ID 200. And so they come into this node. And I have to, and the good thing is, I can send a subset here, I can set a subset here, and I don't care because I can choose an arbitrary matching which path I send where. And now what I simply do is, I send the path that has the higher IDs, I send there, and the lower IDs I send there. And in order to store this, I only have to store the separation. I have to store one value, and this tells me as a routing rule which path I should move upwards and which path I should move downwards. So the disadvantage of this is I can only travel along this matching in one direction. I can kind of not get back. But what you can do is if you have this subset, you compute a matching in this direction, you compute a matching in this direction, and then you still can show that this is an expander. And this is sufficient for our purposes. So what you do is you have all these matchings, you apply this polyrythmically many rounds, and now you have an expander. And in this expander, and this expander is encoded very efficiently, and in this expander now you encode a hypercube. In this expander you encode a hypercube, and this I can do with congestion log squared n. And path of logarithmic lengths. And now you have path of logarithmic lengths. How do you store this? This is easy. Simply the source of the path kind of stores the whole path. These are just log n steps. So you first embed this expander, and then in this expander, you embed a hypercube. And then, unfortunately, the congestion of this whole thing in the end will be log to the 7 or so. And this is only for the case if you just want to communicate between the light vertices. If you can also kind of, if the light vertices are in the majority, you can route all the heavy vertices first to light vertices, and then they use the hypercube on the light vertices. And also, if the heavy vertices are in the majority, you can do something. So this case you can kind of solve. The case that we cannot solve is if I have arbitrary weights. This we don't, if I have lots of weights classes, we don't really know how to do it. But maybe there's an easy way. So this, I won't rule this out, that there is an easy way to do this. So this is kind of the open problems. Can I do this for general graphs? For which graphs do I have a decomposition tree with small degree? And in general, if I can solve a multi-commodity flow problem with some congestion, can I get some solution with small congestion, maybe a little bit larger congestion, and with small routing tables? Is something like this possible? Maybe there exists, one can do something like this. I would not rule it out. That's basically for every multi-commodity flow, you can kind of transform it into something that has a little bit higher congestion and small routing tables. But that's just a question. I didn't think a lot about this. And then, of course, here the question would be what to do in the name-independent case. This also is completely unclear. OK, thanks. Yeah.
I guess one question that came up at our table, so sorry if this goes back to original work or the whole scheme of Oblivious, Racke, and and maybe goes too far on the direction you want to go. But one way to make oblivious routing simpler to implement, so oblivious routing chooses a probability distribution or whatever flow for every sourcing pair.
Yes.
What would happen, or would it be possible to choose a probability distribution for every node of what to do with the next packet at that node, like which edge, how to distribute it between the next edges? Is it possible that such a scheme could also work? That would be very local. Like,
okay, so actually never thought about this. So basically that you don't need to specify a complete path.
that's the question.
But like there was this latent scheme for multi-commodity flow that was sort of that principle.
Yep.
So is this, so for multi-commodity flow problems you can?
I mean, Albert Book Layton has a beautiful paper where they do packet routing this way. So, you know, packets come in at the source at the regular interval, and then every step you forward it in some direction. It's not oblivious because you always look at, you know, if I'm the red flow going from A to B, then you look at how many red neighbors that it's distributed but not oblivious.
Okay.
Right? But it's working in this. You just look at your neighbors and forward it in some direction. I don't know if, you know, we were just thinking of a very simple, compact kind of scene. Random walk tends to get to the destination. I do understand that the uniform random walk is not going to solve the congestion problem. So no, is there possibly a non-uniform random walk that takes care of your thing?
Yeah, so, yeah, okay, I don't know, but I don't really have an answer, but this would, yeah, one should check whether there is a counterexample to this. Thank you for this suggestion. So.
Thank you, Fred.
Yes, so one question that came up at this table was, why are there are so many good theoretical results, but why do we not see them being applied in practice? One thing that we thought about was the interpretability of the results, because you get these routes, but when you are actually applying it in practice, you need some confidence that these routes will work as expected. And I guess that is one thing, but are there any other things that...
The log cube might be a problem.
Yes, yeah.
I'm not sure. I don't think, as a systems person, I'm not sure. I'm super worried about like the asymptotic bounds as long as it computes within like 5 seconds. I'm happy. I'll take it. So I'm not sure. I'm super worried about the log cube. Those kind of like. I mean, if it's
congestion then.
But even that, if it's in practice, it's okay. I think it's probably not that bad.
So
those worst case bounds are like pretty worst case. I mean, probably some corner case.
I have the feeling that okay. I'm a theoretician, so maybe I'm completely wrong, that in practice, if the link load is small, you want to have, if kind of the network is hardly loaded, you want to have short paths. Decrease latency, if the network load is small, then you want to possibly shortest path routing is the right thing to do. Now, what will this do? This will not use short paths, even if it would be a good idea to do so. It also still uses maybe rather long paths if the network is not loaded very much. So possibly in practice, I believe there would be some combination that you use this maybe as a fallback routine or something like this.
That seems counterintuitive. If the network is loaded, by sending packets and making them occupy more of the link, you're increasing congestion. So there has to be some parts of the network.
Yeah, but here what happens is I'm distributing it more. I'm kind of the hotspot is kind of...
Yeah, so it cannot be uniformly congested everywhere. There has to be like some sort of localized congestion.
Yes, sure. I'm not getting to a completely random intermediate node.
play slight devil's advocate with your own work, but maybe a misunderstanding. If you picked objectives, though, that were like convex combinations of load and congestion, you could also get oblivious routings for metrics like that, right?
Convex combinations of
Yeah.
load.
Yeah, if I said I care about mix of load and congestion, your general oblivious routing stuff says you could probably design oblivious routings for that too.
No.
No?
If you want to minimize, so what one might want, or maybe I misunderstood your question. What you might want to minimize actually might be sum of congestion plus dilation or something like this. Yeah. This you cannot do.
I thought you can't be simultaneously good on congestion and dilation, but if your metric is literally the sum.
No, you cannot really in an oblivious way. Counterexample, I give you any network, and then I'm adding edges with very small capacity to a central vertex. So the dilation, the distance is always 2. So now if kind of the load is very small, you should kind of communicate by the center, then the congestion is small because you have hardly any load, and the dilation is 2. But now if kind of the load is high, you should not, because these are so light edges, you should not use them. So then even if you look at sum of congestion plus dilation, you will not be competitive.
Okay, yeah, this is something level more.
So this is a somewhat low-level question, but I'm just curious, in this whole family of oblivious schemes, what kind of computational model for forwarding do you need to assume the nodes are capable of? And I asked this question thinking about these new programmable switches, and as I was listening to your talk, I was trying to convince myself whether or not they could be realized on those switches, but I wasn't quite able to connect the dots down to that. Like when the packet comes in, what are the kinds of operations you need to be able to do to make these?
So first of all, you need to be able to compute the path in this decomposition tree. So the label is just a bunch of bits where you kind of encode the path to the root node in the tree. And then you get the same for the target. And then kind of you have to compute this path.
Will those things be pre-computed and stored in the switch, or you wouldn't dynamically need to compute that, presumably?
I probably would do it dynamically because I have these are kind of pull, look, and bits. Pull, look, and bits. I have to compute a kind of an ancestor in this path. This would be some way to do this. Yeah.
So I have maybe a completely sort of tangential random point. So your model of this hierarchical.
I'm sorry, just to keep us on schedule,
No, okay.
I think we should delay your question until
Okay.
the. Thank you, Harald.